Hello. Give me 1 second. Okay. Hello. Today I'm going to be finishing my 2.1 calculus in a math marathon again. I saw that part 3 did really well, and I saw a bunch of comments asking questions. And yes, I do use a subscription to anyone asking, and it is pretty fair for all the lessons that it contains. For you, there's logic, scientific, computer science, and there's a bunch of subcategories. And just wanted to say thank you, guys. The video did so well, and I'm doing another one. I like doing this every Friday. I probably will do one next Friday. I just like doing this every Friday. It feels nice, and it's perfect. I took off yesterday, so I could have 4 lessons today, so I could finish it up. Because if I had 3, that would be fine, but it would just be a shorter one. The math marathon is supposed to be long. So I'll start one now. So the first thing, this one was with physics. I believe that one. And now we're getting back into math. So we're kind of the same, but physics involves a lot different things too. Okay, optimization. Find extreme values with derivatives, one of the most important uses of calculus. Optimization. We've seen that continuous functions on a given interval have a maximum and minimum value. Optimization is a process of finding these points called extremia. As we'll see in this lesson, derivatives play a staring role in this process. Where are they? I have time for everything else but my math and my Duolingo for Spanish. I'll just have to down this in case I have to write notes. The graph of a function tells us a lot about the maximum and minimum. For example, we can find the maximum and minimum of a graph y equals 3 negative x to the second power. What is the maximum and minimum? I would say this. Well, would there be considered a minimum? Here, let me go with it. I was thinking, but it kind of looks obvious that isn't. From the graph, we can see that the maximum is 3 when x equals 0, and there is no minimum. So the graph continues infinitely downward. We can see this numerically as well. Since x to the second is always non-negative, we have x to the second power is more equal to 0. And thus 3 negative x to the second is more equal to 3. But for very large x, 3 minus x to the second is very negative, so there's no minimum. By definition, a function can only have one maximum and one minimum. Often we want to consider a maximum of a function with a certain interval that has considered value for which changing x in either direction reduces y. These are called local maxima, as opposed to the global maximum that takes the entire function into account. Local minimum are defined similarly. Global maximum is a local maximum as well, so to find a global maximum is surfaces to check all the local maxima along with the endpoint. Yeah, I think I did this in the 1.1. Right now, 1.1 was just in a nutshell, everything. All the basics of it. Or not all the basics, but everything you do in calculus. And then this is talking about, now this is explaining those things more into depth. Because I was learning about limits and derivatives in the earlier one. but it didn't take it that far, like as it is now. Now we're having like a bunch of multiple lessons. Last time I believe I only had 3, so this is really good. How many local maximums and local minimums? So 1 is right there, 2, 3. I think there would be 3 local max. 1, 2, 3. Yeah. Yeah, these graphs going down. The last 2 ones are definitely not. The green points represent local maximum, and the red points represent local minimum. Now, note that the left and right edges of the graph are not local minimum or maximum because the function continues to shrink or grow outside the small window we're looking at above. Since they continue to infinity, there are no local maximum or minimum output points of the diagram. If the graph did end at these endpoints, which often is the case in real-world scenarios, we were looking for a global max or min, these will also have to be considered. If f is a function with a local extreme maximum or minimum at x equals c, then f prime c equals 0. Positive derivatives correspond to places where the function is increasing, and negative derivatives correspond to places where the function is decreasing. Okay. Yeah, I understand. Let me make sure I crop this row out. Just so I can remember. And my notes, I think, come very handy with this stuff. Okay. I don't want to put everything though, because it would be good, but then I would absolutely have everything covered. So I have been putting a lot more pictures, which actually is a lot more better. The beginning I was doing here. And then I got a picture. And then you can continue. And then there's been more pictures. It is easier for me and it gives a lot of info. I'm not sure if all of them are needed, but you could. Okay, let's just track them in different lessons. Sorry. Positive derivatives correspond to places where the function is increasing, and negative derivatives correspond to a place where the function is decreasing. At an extreme, the function is neither increasing nor decreasing, so the derivative outpoint should be 0. Therefore, if function prime x exists everywhere, all the local extreme can be found by setting the derivative equal to 0, solving the resulting equation. As a result, the global maximum can be found by these steps. Yeah, I think I was doing this before in the other lesson. I probably recorded it, so I probably could find it, but I do believe I did. But this is... And don't get annoyed if I put a lot of pictures. I like doing this, and I kind of do commonly doing. Here at this. And here How to find global maximum. I had the uppercase in. Okay, let's continue. Note that setting the derivative as 0 may result in extra points where the derivative is 0 but the point is not extreme. This is fine for our purposes, as we still find the maximum along the values considered, just using a little bit more work than necessary. Extreme can also occur where a function fails to have a derivative. Think of the tip of the absolute value of x. On the interval x union -3, 3, what is the maximum value of the function x equals x to the third power minus -12x? What's the maximum value of the function? Trying to think. I really don't know. Probably an explanation. I'm gonna say 9. 16. Yeah, it was definitely off. The derivative of the function x equals x to the third power minus 12x is, I forgot about the Taylor series. Function prime x equals 3x to the second power minus 12. I like thinking of the Taylor series if you don't understand it, which you probably do if you're watching this. I don't understand that great, but what I do is that it looks kind of like elimination. Like you can feel like as the power goes down, like this, but like you could see -12 goes to -12, then it'll get eliminated the next prime. And it'll go repeating like this. It'll go, I believe it would be 2x, and then it would 2x, just 2x, and then it would just go 2, and then it would be gone. So you can continue. Setting this to 0 gives x equals plus or -2, so that extreme or 2 equals -16, and function -2 equals 16. Testing the endpoints x equals -3 and x equals 3 as well, we see f3 equals -9, f -3 equals 9. So the maximum value of the function is the largest, -16, -9, 9, 16 either, which is 16. Farmer has 100 meters of fencing from which to make a rectangle. What is the maximum area in square meters he can enclose? What is the max? Which he makes a rectangle. What is the maximum area of square meters he can enclose? First step of solving this problem is to figure out what the function will look like the maximum area of a function of what? The maximum area he can enclose. Wouldn't it be 625? I'm trying to remember. I feel like it's either B or C, to be honest. I'm going more with B though. But I don't know, C just seems more informational. Like it would be more accurate or something. D definitely seems like way too much. A seems like way too less. I'm gonna go with this. Okay. Phew. I didn't want to mess this one up. Suppose the rectangle has dimensions x equals width and y equals length. Then the perimeter is 2x plus 2y, which has to equal to 100. In other words, as we solve down here, we could go to y equals 50 minus x. The area of the rectangle is then xy equals x times 50 negative x, which would equal 50x negative x to the second, which we must maximize on the interval x 0, 50. Taking the derivative of a function gives function prime x equals 50 negative 2x. Saying this is 0 gives x equals 25. Then, thus we must test x equals 0, 25, and 50, which gives areas of 0, 625, and 0, respectively. The maximum area is thus 625 meters. This can also be seen from the graph. Okay. We've seen earlier that we can identify local extreme by analyzing the first derivative, but this doesn't immediately tell us which points are local maximum, which are local minimum. By using the second derivative, we can make this determination through the same techniques as before, analyzing whenever the derivative is increasing or decreasing around the local maximum, whenever it is increasing or decreasing around local minimum. Which of these is true? So the second derivative is positive. Negative. Well, you have to think about it. I don't know if this is used in physics, but acceleration is usually F prime prime. That would really affect this. Increasing or decreasing. Second derivative we can make. Integer negative and positive. Get local negative out. So, is it technically is it like deaccelerating? It's positive. I don't think it would be positive. I think it would be this. Negative, positive out local. Trying to see why. I knew the local maximum would be negative. I was thinking about the local minimum. I'll see why. You always have to learn something new. Since the derivative is decreasing around the local maxima, the second derivative is negative out local maxima. This is analogous to the Bohr statement that a derivative is negative when the function is decreasing. Similarly, the derivative is decreasing around local minimum. Second derivative is positive at local minimum. Oh yeah, higher, so they're like opposites. This allows us to use the second derivative to determine whenever extreme is a local maximum or minimum, which is known as the second derivative test. Here, I'm going to take a picture of this and then read the rules. Mm-hmm. Mm-hmm. Mm. No, I see this is correct. Mm. I do global. It's kind of the same. Extreme. Extreme local. Yeah, extreme is a extreme. Certain derivative test. Mm-hmm. Now I'll read them. If the function of prime A equals 0, then check what f prime prime A is. If function prime prime A is more than 0, there is a local minimum. If f prime prime is less than 0, there is a local maximum. If f prime prime is equal to 0, we cannot conclude anything. It may be either. That seems simple. Yeah, I remember that. Like the acceleration in physics. The acceleration. Smiling and sad face. So to find the global maximum of a function, we have two choices. We can either evaluate all the critical points, or we can use a second derivative test to identify the local maximum and only evaluate those. It's not always obvious which one is less work. A box is to be here's the equation. A box is to be constructed by starting with 10 feet and 16 feet rectangular piece of cardboard, cutting out square corners of area h square feet each, and folding the sides upward. What is the maximum volume of the box? So, not 160. That'll be low. Yeah, because what is the volume? I can't fail my math teacher with this one. So, it's a little confusing. Like, I know how to understand volume of rectangle, definitely. But, maximum volume. So, maximum volume. So it would be it has to be this divided by 27. If we calculate what that would be. So, divided by 2700. Well, the whole surrounding would be. I don't think it would be. I don't think it would be this. I don't think it would be that. Just trying to find where these unknown spaces are the open areas. They may be two each. You could always consider. Let me try calculating. We consider this as 12. We consider this as 6. Hmm. 12 times 6. We'll calculate the height. X would be let's say the length. And this would be 2. Two. 24. It's 24 for that. I believe 200. I already know what. Okay. The dimensions of the box are 10 minus 2 height times 16. Actually, I may read this because this contains a lot of description. So I'll make sure I move through it slowly and not read too fast. But you can pause or continue to read with me. I'm just going to read quietly. Sorry that I was quiet for so long, but I'm going to be quiet again. Or I guess I could have technically did if I divide this again. Divide by 2. Yeah. Yeah, I guess because of the primes, I'm like, yeah, okay. I got the primes wrong. Like, the formula decreasing and stuff. I got it wrong. A cylinder area. Okay, I can't get this wrong for my math teacher. A cylinder has a surface area of 96 square feet. What is the maximum possible value of the cylinder in cubic feet? Surface area. Surface area. Christ, just Kevin. Sorry. Keep doing this. $796. Has a surface area. Running the whole thing. Surface area. Here, this is, I wouldn't count this like cheating, but I'm gonna look up cylinder. Their formula. I can't forget. It's a little embarrassing. Okay. Volume equals radius square. Okay. The maximum possible value. You mean it would be basically the same thing as height? It would just be this. Oh, yeah. I see that now. Never mind. I don't even want to look at it. I'm sorry. So, okay, here's another question. I won't fail this, I promise. Suppose you live on a 100-floor building and you're curious how far an egg can drop without breaking. Unfortunately, you only have one egg. You can travel to any floor and drop an egg to see if it breaks, and once the egg breaks, it is gone forever. If the egg doesn't break, you can retrieve it and try again. Assume that eggs breaking only depends on height. For example, if eggs drop from floor 10 breaks, an egg drop from 11 will also break. Conversely, if an egg drop from floor 10 doesn't break, an egg drop from floor 9 would not break. What is the smallest number of times you need to drop the egg to guarantee you find the correct floor? Smallest number? I don't know about 50 or 100. You need to draw it. You find the correct. Well, not 1. I bet it would be 7. It will not break even from the 100th floor. So, well, not even break from the 100th floor. And the 30th and the did not change for P experience. So, what is the smallest number of times? Well, I believe it wouldn't be 1. Because if you dropped it from floor, let's just say 100, and it does break, and you drop it from floor 99, it does break too. So you'll have to continue that for a while. So, I mean, it is based on luck, but a guarantee approximation. Technically, you mean to do all of them. I don't think 7, I guess, then. I thought 150 would be crazy, but still. You probably could split it out by like 2. So I believe 50. You. Sorry, I failed again. Say that your first drop was from floor 10. If the egg breaks, you know the correct floor is somewhere below 10, but you don't have an egg to work with anymore. The same logic applies a floor above the first. So your first drop must be on the first floor. Similarly, your second drop must be on the second floor, continuing. All you have to drop is from 100 floors, making this a minimum number of drops. This guarantees success. With 2 eggs, the problem becomes more interesting. Or you could always do primes vibes. You live on a 100-floor building and want to find the lowest floor at which a dropped egg will break, using 2 eggs as few drops as possible and assuming that broken eggs depend only on height. One strategy is to drop the first egg at K floor until it breaks. When the first egg breaks, we'll have a range of K minus 1 floors checked, which should be done with the second egg as in the last problem. For example, if K equals 3, the first egg could be dropped at the 3rd, 6th, 9th floors would break on the 9th floor, and the second egg would be then dropped at the 7th and 8th floors, breaking on the 8th floor. We will be able to conclude that the 8th floor is the first floor where the egg will break. Using our strategy for the best value of K was the smallest number of drops to find the correct floor. So, we saw. Let me read this again. Correct. So we have 2 now. 100 floors. Smallest number. I feel like it'd be 24, but I also don't. And I didn't look. I forgot. Well, I'm gonna look again. What's for that? I really didn't think it would be 10, though. It better not be 10, though. I'll be disappointed. Here, I'm just gonna do some random things. See if it even gives anything close. I'm gonna say 24. Close, but not close enough. This is confusing. Probability. I guess you could do some stuff with that. That shouldn't be a lot. The first phase of the strategy will take 100 over k drops, since we're checking every k's floor. Once we find the floor and the egg breaks, the second place of the strategy will take k minus 1 drops. For example, with k equals 4, we check floors 4, 8 to 100, which could take 25 drops. Worst case if the egg doesn't break on floor 8, 96, but breaks on floor 100. The second phase will then check floors 97, 98, and 99 as expected. Therefore, the total strategy takes 100 over k plus k minus 1 drops, which we want to minimize. Taking the derivative gives k to the second minus 100 over k to the second, which is 0 when k equals more or less than, positive or negative 10. Of course, k equals negative 10 makes no sense, so k equals 10 is a critical point. The endpoints are k equals 1 and k equals 100. Both give 100 drops, which makes sense between k equals 1 is essentially strategy from the previous problem. So k equals 10, d minimizes the function and takes 19 drops. You might have noticed a potential issue here. We're minimizing the function 100 over k plus k minus 1 over the continuous region of 1 is less or equal to k is less than or equal to 100, when in fact k must be an integer for the strategy to make any sense. So we're solving a discrete problem using only continuous methods, which requires slightly more rigorous argument to formalize. Still, that's pretty cool. We found the best value of k in this particular strategy. Are there more complicated strategies, perhaps involving dropping every k floors when k is changing, that might solve the problem with fewer than 19 drops? There are. This gets outside the domain of calculus and has to do with the theorems of algorithms and dynamic programming. That seems confusing, but also interesting. We'll finish this lesson. 3 more to go. And then the implic differentiation, which means compute rates of change of related quantities. That sounds interesting. Let's see that. Implic differentiation. Up until now, we focus on derivatives from a functional perspective, taking a function x and writing the derivative as function prime x. However, the scientists often focus on derivatives following a variable perspective, writing the derivative as the derivative y over derivative x instead of f prime x. I don't know, we're getting into this. I've seen these all the time. This way of writing it, I think this is used more too, especially in the sciences. This notation is slightly clunkier, but emphasizes the rate of change interpretation of the derivative. This is really saying change in y over change in x. But it's derivatives. This emphasis is important for problems involving many variables, as it's easier to keep track of various derivatives when written in the exponent derivative y over derivative x form. For instance, give a sphere with radius r, volume v, and surface area s. We can write v equals 4 over 3 pi radius cubed, and s equals 4 pi radius squared. And this one volume is the And I guess never mind, these are just the formulas. Though it may not look like it, this defines volume as a function of x, s. So it is meaningful to ask what derivative of v over derivative of s, like change in volume per change in surface area is. In variable notation, like chain rule is natural. Derivative of x times derivative of x over derivative of y times derivative of y over derivative of z equals derivative of x over derivative of z. So just combine. This is useful for the introduction. Let me actually take a picture of that. And hopefully I'm taking pictures of stuff that isn't incorrect or anything. I know this is, but sometimes it's like this may be wrong in certain situations. Okay. This is useful for the introductory problem where V, S, and R are the volume, surface area, and radius of a sphere, respectively related by volume equals 4 over 3 pi radius to the cubed, and S equals 4 pi radius squared. Okay, what is dV? Derivative of volume or derivative of radius, a sphere. Surface area. Was the derivative? Let me see. For the two equations, it's relatively easy to find derivative of v over derivative of r, derivative of s over derivative of r. How can these be combined to get the desired answer? That's pretty easy, but let's see this. Divided by itself. I wonder if we can insert this equation into the calculator. Let me just close these really quickly. We could. Hopefully I'm not like messing up like the whole math. I'm not messing up with anything. Because this must be like cringy to like actual calculus students. Considering. Wait a second. I'm so used to you doing this, but with actually having the numbers to solve for this. It's we're doing volume over the surface area. So let me see if I could solve this. Let's just say the radius. So we can calculate that. So we have that. That would be one. Or the same answer. The chain rule follows us. The chain rule allows us in many circumstances to think of a. Those are the same things. The chain rule allows us in many circumstances to think of a derivative of y, derivative of x as a ratio of two quantities. For example, the relationship between y and x is interval, as we can write y as a function of x or x as a function of y. The chain rule implies derivative of y over derivative of x equals 1 over derivative of y over derivative of x over derivative of y. Which is very much like the fraction rule. A over b equals 1 over b over a. In the chain rule itself, we can imagine the dy terms as canceling just as b cancels in. With this in mind, we can see that 1 over derivative of x over derivative of r equals this. So this would equal derivative of r over r, and then we could do second power over 8 pi, and then radius. Okay, I slightly understand it now. Yeah, I understand it. So, I'm gonna take a picture of this just because, so I can remember the formula. Maybe one time I'll just come back to these notes and it'll be very useful. I'll be like, oh, thank you. I should really thank myself. I took all these pictures, which did feel like a waste of time then, but now it feels very useful. And I've been doing a lot more. And help me with these, though. Sine, cosine, or prime, and tangent, intersect. And then continue. Why have these lessons felt so long? I feel like they're feeling longer for some reason. Usually functions are described explicitly in terms of their variables. For example, y equals 1 over x or y equals sine times 1 over x to the second. But we could just as easily give an equation like xy equals 1 or xy plus y to the second equals 2, which could imply describes y as a function of x. In the later case, we can still find the derivative of y with respect to x using implicit differentiation, which takes the derivative of both sides of the equation with respect to x and solves derivative of y over derivative of x. For example, suppose we wanted to know the tangent line to a circle, which is described by equation x to the second plus y to the second equals 25. We can see in this. Using our previous techniques, we will have to write y in terms of x and take the derivative of the result, which is more complicated. Try it. But with implicit differentiation, the process is much easier. And then we can see by here. Know carefully where we use the chain rule. Let me see. There it's used. There it's used. And then there. The derivative of x to the second with respect to x is just 2x. But the derivative of y to the second with respect to x is 2y. Derivative of y over derivative of x, because the chain rule. Derivative over derivative of x times y to the second, equals derivative of y over derivative of x, derivative of y, y to the second. We add those in. We can see that the result contains both x and y. This is typical and just means that evaluating the derivative at a particular point will need both coordinates instead of just like the x coordinate. For example, the slope of the tangent line at the point 3, 4 is negative 3, 4. Suppose xy equals 4. What is the derivative of y with respect to x? That is, what's the derivative of y over derivative of x at the point 1, 4? What is the derivative of y with respect to x? At the point 1, 4, or 1 over 4. It would just be rather the opposite. Wow. Would they just be technically the same thing, though? You see. Before we differentiate both sides with respect to x. This linear approximation. Continue. Oops. Y equals 4. And then, let me see where they use the chain rule. There they use there. Now it's just a matter of plugging in the point 1, 4, which gives a derivative of negative 4 over 1 equals negative 4. Just for practice, note that if xy equals 4, we can write y equals 4 over x. The derivative of this x point function is negative 4 over x to the second. When x equals 1, this gives negative 4 just as before. Implicit differentiation and the new variable notation is useful when there are many changing parts in a problem. For example, a constant filling up a cup with water at a constant rate. The cup is perfectly cylindrical. Understanding the height of the water is easy. It's linear relationship with time. But if the cup were a cone, the situation is far more complex. Earlier on, the cup will fill quickly, but over time it will take longer and longer for the water to rise. Yeah, we can see as more like deceleration. Well, also based on the mass. Wonder if we could relate how in a cylinder you could just do the times 1 over 3 and receive a cone. It's a relative size. However, we do know how the volume and the heights are related. We can write down a formula relating them. We take the implicit derivative with respect to time of that function. We'll have an equation in terms of volume, derivative of volume over derivative of time, height, derivative of h, and derivative of time. Since we know volume, derivative of v, and derivative of t, and h, we can solve for derivative of h over derivative of t. A spherical balloon is being thrown using... Okay. A spherical balloon is being blown up at a constant rate of 5 centimeters cubed a minute airflow. At some time, the balloon has a radius of 5 centimeters. At that point, how fast is the radius of the balloon increasing? Assuming the balloon is a sphere at all times, as the balloon is uniformly compressible. as we can see before. Formula. I don't know why I always forget. It's always a cylinder formula. I forget. But okay. You can see it's 20 room. Passes a radius. Centimeters. It's saying a constant. What is the radius being? Right, but the radius. Rain. Would it be divided by pi? So would it be 5? Or would it be 1 over 5 pi? The balloon is spherical. Is being blown up at constant rate of 5 minute airflow. The balloon has a one. Pass it. It may be a little less if you think about it. Maybe 1 over 5 pi. I really don't know. It's so easy with the height, even though this is solvable. The radius of 5. I really don't know. I feel like it wouldn't be 1 over pi centimeters a minute. It just doesn't feel like it would make any sense. Has a radius of 5. Type of circumference. The radius. Yeah. I just feel like I don't know what the radius would be. Yeah. I know it'd be little, but it's gotta be this then if it would be little. I guess it was even little, very little. So we can relate the volume with respect to time, gives us derivative v over derivative of t. It goes forward 3 times 3 r radius per second. Or chain rule again. 3 equals 5 by definition. The volume is increasing again. 5 equals 100 pi derivative. So if we combine those, applying it. I should have realized. I'm gonna take a picture of that. Sometimes I just feel like I probably could solve those, and then I just can't remember. So I have to remember literally everything, all the derivative rules, all the chain rules. Make sure how I can insert that. So now, this better just be Pythagorean theorem. Okay, we done. A 5-foot ladder is resting on a wall so that the top of the ladder is 4 feet above the ground. The bottom of the ladder is 3 feet from the wall. At some time t0, the ladder starts to slip down and the wall so that the top of the ladder falls at a constant rate of 1 feet a minute. Ignore possible acceleration. When this happens, how fast is the bottom of the ladder slipping from the wall if it stays remain in contact with the ground? So fast, just compute x equals 0, assuming x equals 3 y team. How fast is the bottom of the ladder slipping away from the wall? We're gonna be like this then. I feel so dumb not doing this. But 4 or 3 means it's falling out. 1 point. Constant rate. Just want to just be 3 over 4. I'm not even gonna read. I'm just cringing at how bad I was at it. 2 cars start driving at the same time, originally with the first car shown as 80 miles directly north of the second, shown as blue. The first car travels south at a constant rate of 40 miles an hour, while the second car travels east at a constant rate of 30 miles an hour. After 1 hour, how quickly is the distance between the 2 cars changing? The second car travels at a constant rate of 30. Increasing. Her car is right 80 miles directly north. Increasing by 8. Mm-hmm. 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 Mm. Mm-hmm. And they have to be getting closer. Increasing by 8 miles per hour. After 1 hour. So, just say, so. 20. Here, give me a second. I'm gonna calculate this. What would be the increase? I'll be right back. Well, I don't think I have a pencil or anything around here, so I'll try to calculate here. So, what would... So let me just do... I can probably write here. And just plus... Here. Equal. Equals certain. So we eliminate. What would x have to equal? It was the right way around. That way. If I thought I deleted all of this. It was right for a second. So you can eliminate that. So it would be 8. I'll give up with this. I'll just look at it. That's fine. Let's see. It goes. Yeah. Pythagorean. Just please give me Pythagorean there. The lamppost 15 high and fixed on the land walking over front. We're trying 6. How does a man measure his? How does a man? Bearing. I believe it would be increasing, not 4 feet. That'd be amazing, but maybe decreasing actually, would it? Technically. It doesn't mean he's growing. He's 10 feet. Growing. It's gotta be fair over 2. No, I give up. Sorry, I'm not gonna look at. If you want to pause the video, you can. I'll read quickly, but I need to do better on the next lesson. I need to redeem myself. Majorly. I need to redeem myself. Like, really. And here it is. And, no, I'm done. I'm sorry, I literally did so bad. I'm gonna need to recover. In the Hopticals rule, come full circle and use derivatives to find difficult limits. So here we go. The Hopticals rule. This lesson will look at some difficult limits and introduce a rule as known as the L'Hopital's rule. I can help compute them in some situations. Here's a simple motivating example. Consider the limit. Limit of x is 2 to x to the second negative 4 over x to the second minus 5x plus 6. The numerator and denominator both approach 0 and x is 2, so that is yet another appearance of the intermediate form, 0 over 0. We already know how to evaluate this limit by factoring the polynomials on the top and bottom. I'm going to negative 3. Computing those. Yeah, that's it. We're allowed to cancel x negative 2 because the values of x that matter for the limit computation are the value in the interval around 2 but not including 2 itself. But this factoring trick only works in special cases, that is, when the numerator and denominator are polynomials. Is there a way to see what the limit is that will work more generally? Suppose that we have 2 differentiable functions, f and g. We want to compute a limit for the form limit x is a, function x minus function a over g x minus ga. Divide the top and bottom of this fraction by x minus a. Function x minus a over x minus a over gx minus a. What does this equal? So we eliminate. Which is equal 1 if x is a. I'm already, come on, please, let me continue. I just need to really think hard, not rush through it. F prime a divided by g prime a as long as g prime a is not equal to 0. Top of the fraction is the limit of the definition of derivative f prime a. The bottom is the limit definition of g prime a. So as long as the bottom is non-zero, the limit of the quotient is true on the quotation of limits. Suppose we have 2. Here, let me take a picture of this. Suppose we have 2 differentiable functions, function g and gx, with function a equals function g equals 0, and you want to evaluate limit of x is a function of g over function of function of x over function of g. And we can see the chart. And then the intersecting a, or the limit. If we zoom on the graphs of the functions near the point a0, it will look more like lines. The limit of the ratio of the two functions there should be the same as the ratio of the slopes of the lines. This is the ratio f prime a divided by g prime a, so that we got in the previous problem. Another way to see that in the equations of those tangent lines respectively, y equals f prime a times x minus a, and y equals g prime a times x minus a. The ratio should be approximately equal to function prime a times x minus a over g prime a times x minus a, or equals f prime a over g prime a. We could think of this as a, here, let me just write this. You have to equal a. We can think of this as a generalization of the polynomial case, where the factor x minus a can literally be factored of both sides. This more generally explanation takes out approximate factors of x minus a on both sides to achieve the same result. Suppose that f and g are differentiable functions with fa equals ga equals 0, and that g prime a does not equal 0. Then the argument shows that the limit of xa function x over function g equals limit xa function x minus function a over gx minus ga, which equals f prime a over g prime a. This is a special case of the useful in fact known as L'Hopital's rule. It's often useful for evaluating the derivatives. Let me take this picture. Okay. Evaluate this limit without factoring. Limit of x is 1, x to the 8th plus x to the 7 minus 2x to the 6th over x to the 3 minus 2x to the 2nd plus 1. Evaluate the limit. So we can eliminate here. I'm not certain, but sure. I don't want to mess up again, though. So I'm gonna look very carefully. This may take a minute for me. And then that limit of x 1. So. You may just be Notice that both the top and the bottom approach 0 as x is 1. L'Hopital's rule gives limit of x is 1, function g over function x equals limit of x is 1, function prime x over g prime x equals function prime 1 over function prime, or gx. And then, we go back to this, and we could solve using that in this equation. And then 8 plus 7. Oh. Oh, right. I understand this now. Finally. Yeah, simplify. L'Hopital's rule. Yeah, I'll take another picture of that. L'Hopital's. Let me see if I can get his name actually right. Let me see if I can consider his name right. So it would be L prime A 0. In the case of useful fact. Let me see if I. Oh yeah. Okay. Good. It doesn't even have it. So then I'll insert the other picture too. Which is the actual room. I forgot I crop it. I'll just leave it and crop. Sorry, give me a second. Okay. I'm gonna crop this one. Note that we removed that condition that g prime a is not equal to 0. In fact, sometimes we find out that limit of x to a, function prime a over g prime a, is also an intermediate form of type 0 over 0. And to calculate its limit, we apply L'Hopital's rule again. So the L'Hopital's process of taking the derivative of the top and bottom can be iterated until and if we find a final answer. Compute limit of x is 0, 1, negative cosine x over x to the second. So I wonder if I've never done this before. I wonder if you can insert that into a calculator like this. Let me see if I can. Cosine 0 divided by 0 to the second. Well, that definitely just proves. Let's just do, what would cosine 0 be? 1. So 1 minus 1 over 1 over 2? Yes. Losing streak. You see why? The top and bottom both go to 0, so L'Hopital's rule allows us to convert the limit to Lx0 sine x over 2x. This is also an intermediate limit of the form 0 over 0. It can compute by applying L'Hopital's yet again. The limit of x is 0 sine x over 2x equals limit of x is 0 cosine x over 2, which should just be that. So we could convert the limit to a derivative form. It turns out the result of L'Hopital's rule can actually be applied to another common intermediate form. The limit of x is a function x over gx is one of the intermediate form infinite over infinite or negative infinite over infinite, etc. Then equals limit of x a function prime x g divided by g prime x whenever the latter limit exists. And many other intermediate forms can use L'Hopital's rule as well by turning them into quotients. What is the limit of x is 0 positive x in? Let me get a hint there. Plugging in x equals 0 gives the intermediate form 0 times negative infinite. Let's see. I wonder if this has a... Here we go, a second. Alright, sorry for the pause. My mom was asking me something. Yeah, and not a great time, but it's fine. Equals 0 times negative infinite. What is the limit? I think it would be 0. Okay. Now the limit of the form negative infinite over infinite taking the chart to attack is... okay. I understand now. It's not that bad, I guess. I just didn't remember the rule so I could solve all this. For any a does not equal 0, we can prove that a to the 0 equals 1 with the rule of exponents. However, we can't do the same for 0, 0, because the proof that a to 0 equals 1 involves division by a, which is impossible if a equals 0. Still, it's conventional in mathematics to define 0 to the 0 to be 1. Why? Well, let's rewrite the result of the last problem like so. 0 equals the limit of x, 1, x in, x. We could simplify it, and then simplify to in, limit x to 0, x to the x. The middle equality comes from the power rule of logarithms. The last equality is due to the continuity of the natural algorithm. Exponenting both sides of 0 equals in limit to the x to the x over x to 0 gives us e to the 0, which equals 1, which equals in limit in the equation below. Above, technically. Which would simplify to the limit of x to 0 plus equals x to the second. As we get closer and closer to 0 from the right, x to the x gets closer and closer is 1, and that's why it makes sense to define 0 to be equal to 1. So, to pause my video, let me see how much I've done. You guys probably know, but I don't. I've done quite a lot. Still going strong. There are some common pitfalls that the beginning users often run into. For instance, L'Hopital's rule starts with a fraction function x divided by gx and says that its limit is, with the correct assumptions, the same as the limit of function prime x divided by g prime x. That is, the conversion process involves taking the derivative of the top of the derivative of the bottom. Note, this is not the same as taking the derivative of function x divided by gx, which by the quotient rule is function prime g times gx minus function g prime x over gx to the second. The limit of this quality has nothing to do with general with the limit of function x divided by gx. Another common misconception involves forgetting the preconditions for L'Hopital's rule. Compute this limit. Involves forgetting the preconditions for L'Hopital's rule. I think it would be limit is 0. Which is 0. Now live in bed. Plugging in 0 gives 0 over E0, which equals 0 over 1, which just equals 0. Easy as that. We see the limit of a quotient and immediately use L'Hopital's rule. Taking the derivative of the top over the derivative of the bottom gives limit of x0 1 over e to the x, which equals 1 over e to the 0, which equals 1. Why is this wrong? Because the prerequisites for L'Hopital's rule have not been satisfied. The original limit must be an intermediate quotient of the form 0 over 0, or positive or negative infinite over positive or negative infinite. If the original limit is not of that form, the result fails dramatically. Finally, we will note that L'Hopital's rule also works well when taking limit of x is infinite. That is, it follows us to evaluate limit of x is infinite function of x over gx. Let a be a real number. For which values of a is it true that limit of x is infinite I in x, or x to the a equals 0? If the x limit is infinite and equals 0, all a is greater or equal to 1. And greater or equal to x. Let's calculator help with any of that. I don't believe so. All a doesn't seem right though. All a. Yeah, none of these equations fit more than 0, at least. I don't know, it has to do something. I was thinking A or the last one. Or E, technically. But I guess I was wrong with either. I knew it would be something related to 0, but that just didn't satisfy me for some reason. If a is less than 0, then x minus a I x is a product of two functions going to infinite. So it goes to infinite. If a equals 0, then we just have I and x should go to infinite. Other hand, if a is more than 0, then the quotient form infinite over infinite. So L'Hopital's rule gives, as we see, by 0. The fact that the limit is 0 means that the denominator dominates the numerator as the x gets large. that is I in x is eventually smaller than x to the a. For any positive a, even a equals 0.0000001. So I in x goes to infinite, but it goes there very, very slowly. We claim that exponentials always dominate over polynomials, but we didn't say why that was true. Armed with El Hapto's rule, we can now see why. For which real numbers a is it true that the limit of x is infinite, x over a over e over x equals 0. If x is a, actually anything. All a, would that technically work? All a equals 0. I saw in this one, which is a total different equation. Maybe just opposite. Okay, here I'm gonna read it really quickly, but I feel like I always have hope in something and I just switch it. It's always wrong. Yeah, that's basically it. So that was interesting. El Hapto's rule seems very useful. A lot to simplify things. It's not very simple, but it makes it simpler. And it does help with those. There's just so much rules. It's always hard, like which one is this, which one is that. That will be it for this lesson. And we have one more lesson to do before we finish this 2.1 calculus fundamentals. Antiderivatives and integrals. So maybe this will just be like a wrap up. Or just glimpse the next, which will be just like a wrap up on this. Glimpse the next step on the calculus journey. So this is last lesson. This lesson will introduce antiderivatives or integrals, which fill in these gaps and form another major pillar of calculus. To understand what antiderivatives are and how they're useful, let's look at a motion problem. Oh yeah, I remember this. I've seen this before. They show us this. Suppose a cannonball is fired directly upward, a speed of 10 meters a second. If the gravity is the only force acting on it, it has a constant acceleration of 10 meters per second squared. If you can see what I mean. Then it decreases. I usually accelerate right. What is the velocity vt as a function of time t? So vt acceleration time t velocity. So acceleration is negative 10. So it would be this. Opposites, I guess. In general, acceleration is the continuous rate of change of velocity. Since the cannonball experiences a constant acceleration, vt changes at a fixed rate for each time t. The only function that change at a fixed rate are linear ones. Vt equals mt plus b. The slope is equal to the acceleration negative 10. The ball is initially... I should have saw that. The pure big graph right there. Here's another way of phrasing the last problem. What's the function vt that has derivative negative 10 also satisfies v0 equals 10? Answering these questions means extracting vt from its rate of change v prime t equals at equals negative 10. So we see that reversing a derivative is a very important process to master if we want to apply calculus to the real world. Let's step away from Arcana for a moment. Let's think how to undo derivatives in simpler scenarios. First, we need some notation. The symbol for antiderivativism is this. dt, and function t dt is a function whose derivative is ft. So we just put this equation. So this ft gt equals ft. So let me crop the picture out to make sure I have it. Yeah, I don't know why it's mistaking it. I just hate that one. Why does it hate it? I really don't like how I just... Yeah, I'm tired. Crappy. You can see it in this. Look at this. Where C is called... Okay. Now, if we want two antiderivatives of ft, there can be differ by a constant. So we write. Now we'll take another one. Where C is called a constant of interrogation, an unknown, useless, given more info. Oops. Which option represents the most general antiderivative function of t equals 1? So what would this be? Function t plus c. Okay. Suppose function of t equals t. Find the most general antiderivative function of t. 1 plus c. But equals function. Wouldn't it just be the same? Function of t equals 1, or would it be opposite? Okay, I'll look at the explanation. The power rule of differentiation tells us the derivative of ta decreases by the exponent by 1. Since anti-differentiation is the opposite of differentiation, we expect derivative of t to increase the exponent by 1, as we see here. To figure out a, we take the derivative of both sides. And then, let me read this. Comparing coefficients, we see that a has to be 1 over 2, so this equals this. It's in this equation. Sorry if I'm reading too fast. I'm just rushing through. I usually get a little faster when I'm almost done with this just because it feels so long. Because differentiation and anti-differentiation are so closely related, they share many properties in common. For example, derivative or derivative of t function t plus gt equals a function prime t plus g prime t, or kind of the same, which function t plus gt dt equals function t dt plus gt dt, or just splitting them apart. And d over dc cft equals cf prime t cft dt equals cft dt. The constant of interrogation is lurking in the shadows. We don't write it explicitly just for convenience. Antiderivatives rules such as these allow us to break complicated problems down to simpler pieces, as we're about to see. Let's return to our Campbell problem. Earlier we showed that Vt equals negative 10 plus 10. The velocity is an continuous rate of change. The height above ground level. Ht, that is, h prime t equals Vt. The graph above Ht is spotted in blue. The green tangent line has slope equal to Vt. And you can see that. Using the rules of anti-differentiation to find Ht if the Campbell is initially launched 2 meters above the ground. This is going to be hard. Actually, 2 meters above the ground. Just like this. So it is launched initially launched 2 meters off the ground. I need one of these. I think it would be this. Since h prime t equals vt, we know that h prime equals vt dt, which equals negative 10t plus 10 dt. Up to the constant of interrogation, the velocity is a sum of 2 pieces, negative 10t and 10. So you can write ht equals negative 10t dt plus 10 dt. We can move constants outside the antiderivatives, so we find ht equals negative 10t dt plus 10 1 dt. The advantage of writing the antiderivative of vt this way is that t dt and 1 dt are easier to evaluate. In fact, we already computed these integrals. Ht equals negative 10 times 1 over 2t to the second plus 10 times t plus c equals negative 5t to the second plus 10t plus c, which, when we exponentially write out the constant of the integration, now that the antidifferentiation is done, To fix C, we can use initial condition that h0 equals 2. And then we can go here, which, as we saw, it's plus 2, and then that's how we do that. Now that we... What is this candle? Now that we know the height of the candle, we can compute interesting things, like how far it travels between the launch and maximum height. This is a different one. I don't know who drew this. Isn't this a different equation? Oh, let T max be the time at which HT reaches its max. Wait. Let's get its max really quick. Which is 7. Reaches in max. We decorate the antiderivative by writing distance traveled equals HT max minus H0. And we can simplify it below. This is called defiant integral. Synonyms with antiderivative. Find the value of the definite integral. So its max is... Would it just be 7? Minus H0. Let me see. Here in the max one, I'll say 2, 0, 0, T max. This is sincerely confusing. And, oh yeah, the starting point. That's why. The maximum and the... Okay. Now, I was like, what is going on? Okay, now I understand. It turns out that HT max minus H0 equals T max 0 H prime T generalizes to FB minus FA equals BA F prime T dt. The simple formula is one of the most fundamental results of calculus. It is key to computing many interesting defined integrals that appear in geometry, physics, and engineering. To learn about these exciting applications and gain more experience with integration, check out our course on integral calculus. Well, I may check that out. And there we go. Fundamentals. Oh, never mind. That's literally I have to do integral calculus. But I'm going to check that. No, I can't. So now we're integral calculus. Which lessons are there? I mean, it's a pretty decent. How far am I in this again? I think I've only done 2. Yeah. There's multiple in certain levels. Yeah, this was calculus in a nutshell, and I finished fundamentals and integral, multiple calculus, linear algebra, vector calculus. And that's... Yeah, let me go back to that. Where was it? And then that's it. So, thank you so much for watching. I appreciate it. I know not much people watch to the end. And this video probably will be cropped a little because of that pause I had to do. So don't worry about that. Well, I want to say thank you for watching. I appreciate it very much. I hope you come again soon. I will try and make more videos, but probably will take a break over the weekend like usual. And I say thank you for watching, and I sincerely appreciate it. Goodbye, and I hope to see you the next time I make a video.